One of the wildest things Interstellar does is make Einstein's relativity feel like heartbreak. One bad landing that lasts a couple of hours steals decades from the people waiting. That isn't a metaphor. It is the plot's central machine. The story begins with a quieter kind of apocalypse. Earth is not exploding. It is wearing out. Crops fail, dust gets into everything, and even curiosity starts to look wasteful. Cooper is a pilot trapped in a farmer's life until his daughter Murph notices something impossible. Her bedroom seems haunted, not by ghosts, but by gravity acting strangely. That detail matters, because gravity is the film's chosen lever. Not lasers, not warp engines, gravity as the curvature of space-time. The movie commits to the idea that space and time are not a fixed stage. They are part of the machinery, and they can bend. From there, the first big leap arrives near Saturn. A wormhole appears, like a clean shortcut punched through the universe. The important point is that general relativity does not forbid weird geometries. In the math, space-time can be shaped into structures that connect distant regions. But allowed in equations is not the same as easy in nature. A traversable wormhole has to stay open. It has to avoid crushing tidal forces at its throat. It has to let matter and light pass without collapsing. That is a taller order than making a black hole, because black holes form readily. Stable wormholes do not. Interstellar solves that problem by handing it to unseen engineers. The wormhole is said to be placed by extremely advanced beings, later implied to be future humans. As a narrative move, it's clever. As a scientific move, it's a transfer of debt. You are no longer asking whether NASA can do it. You are asking whether any civilization can manipulate space-time like infrastructure. The next key choice is Gargantua, the black hole at the center of the target system. It is not a generic black hole. It is a rotating supermassive black hole, what physicists call a Kerr black hole. That single adjective, rotating, quietly carries a lot of weight. Rotation changes everything near the hole. Space-time itself gets dragged around, a phenomenon called frame dragging. The region outside the horizon has an ergosphere, where standing still is not an option. Most importantly for the plot, rotation shifts where stable orbits can exist. If Gargantua were non-rotating, the innermost stable orbit would sit farther out. The film needs a planet to orbit extremely close, without immediately spiraling into destruction. A near-maximal spin gives the story more room. It does not make the setup comfortable. It makes it barely defensible, in the way a tightrope is defensible. Gargantua is also where the film earns real scientific credit, with its visuals. The black hole is not shown as a dark ball with a neat ring. You see a glowing accretion disk, and you see it distorted. Light bends around the black hole, so parts of the disk appear above and below it, like a warped halo. That is the right intuition. In strong gravity, space behaves like an optical system. Light follows the geometry, so the image you see is a map of curved space-time. The film simplifies details for clarity. A fully realistic disk would often look more asymmetric, because the side rotating toward you is boosted brighter. Still, the core idea, lensing as geometry made visible, is unusually faithful for a blockbuster. Now we reach the scene that turned relativity into dinner table conversation. Miller's planet. The claim is blunt. 1 hour on the surface equals 7 years for someone waiting farther out. That is a time dilation factor of roughly 60,000. The direction of the effect is correct. Clocks deeper in a gravitational well run slower, compared with clocks far away. Relativity does not hand the universe a single universal time. Time depends on the path you take through space-time, and the gravitational environment along that path. Interstellar weaponizes that fact emotionally. Cooper does not merely miss time, he takes a route where his own clock advances less. When he returns to the ship, the messages are waiting, and the people in them are older. The science is not garnish, it is character damage. The problem, of course, is the magnitude. To get that huge factor, Miller's planet must orbit extremely close to the horizon, and Gargantua must be enormous and spinning near its limit. A supermassive black hole helps, because tidal forces at the horizon can be gentler than the popular spaghettification image suggests. Bigger holes have weaker tidal gradients at their edge. Even so, a stable, ocean-covered planet in that position is an extremal case. It is not casual Hollywood randomness. It is a carefully selected edge scenario, but it is still an edge scenario, balanced on multiple just-so conditions. Then the film adds those towering waves, which are unforgettable and physically awkward. If the waves are meant to be tides raised by gargantua, they should behave more like broad swelling and lowering of ocean levels, not like kilometer-high moving walls that chase you.
Turning tidal distortion into a traveling breaker is cinematic shorthand. It communicates danger. It does not read like realistic oceanography. There is also the mission planning issue. If every minute on the surface costs days outside, you don't stroll around to find out what is happening. A real expedition would treat that descent as nearly unapproachable, unless the data beforehand were overwhelming. The film needs discovery by experience, because that is drama. Science would try to buy knowledge before paying time. From Miller's Planet, the story slides into a broader habitability question. The movie presents multiple candidate worlds near a black hole system, as if the neighborhood offers a menu of almost homes. That generosity is one of the softer spots in the science. Black holes are not stars, at least not in the steady habitable zone sense. A planet needs a reliable energy source. A black hole can have an accretion disk, but accretion disks are messy. They can be violet, variable, and rich in high-energy radiation. If the disk is dim enough to be safe, it might not provide Earth-like warmth. If it is bright enough to heat planets, radiation and variability become a serious hazard. Habitability is also not a label you slap on from a single signal. It is a systems property. Temperature, pressure, atmospheric chemistry, radiation shielding, orbital stability, and geology all matter over long time scales. In the film, Miller's world and man's world feel less like plausible settlements and more like judgment traps. They test the crew's choices, not the universe's generosity. Where Interstellar stays grounded, again and again, is in how it treats mechanics. The docking sequence after the Endurance is spinning out of control is built on a real idea. If you dock with a rotating structure, you must match its rotation. Otherwise, the relative motion rips you apart. The scene heightens tolerances and timing, because it is cinema. But the problem it identifies is the right one: inertia and relative angular velocity, not heroic steering in a vacuum. All of this makes the final leap stand out sharply. Cooper falls into Gargantua, survives, and enters a constructed higher dimensional space, a tesseract shaped like Murph's bedroom across time. Inside it, he uses gravity to knock books, shape dust, and finally move a watch hand in coded pulses. That is the film's biggest scientific liability. Gravity becomes an information channel, aimed deliberately backward through time. Not just a mysterious influence, a programmable modem. Once you can send a message into your own past, you invite causal loops. The information seems to have no ordinary origin. Murph solves the equation because Cooper sends data. Cooper can send data because future humans built the tesseract. Future humans exist because Murph solved the equation. The loop is emotionally satisfying. It turns love into mechanism. But physics does not currently give us an experimentally grounded way to send deliberate, information-rich signals into the past. General relativity allows strange causal structures in some mathematical solutions, and rotating black holes have rich internal geometries. None of that translates into a pilot can survive inside and tap out quantum data through a wristwatch. So the best way to read the ending is as mythic engineering, wearing a relativistic costume. The film earns its right to dream by doing so much else with discipline. It knows which parts of Einstein to respect before it finally asks for one extra miracle. One more realistic insight is easy to miss because it hides under the spectacle. The movie's heroism is not mainly punching or shooting. It is measurement, data, Murph's equation. A civilization does not escape by being brave. It escapes by knowing enough to build something that works. If there is a single takeaway worth keeping, it is this: Interstellar makes time and gravity feel personal, and once you feel that, space stops being a backdrop and becomes a consequence.